Okay, so in these notes, we're going to finish 9.1, we're going to talk about errors, and then we're going to move on to actually carrying out a hypothesis test for proportion. To review the basic idea, this was the first example we did. There's some claim. The claim was 16.7%. We took a sample, though, and we got a sample of 12%. And so the question is, why is that the case? Why did we get a sample that was less than what the population claimed to be? And so the idea that we've been looking at is you're going to find what is the likelihood of getting that sample if the null were actually true. That's what we call a p-value. So then we looked at how to set up hypothesis tests, and we talked about you're going to calculate this p-value, this probability. There are two different decisions that can be made, bless you. If your p-value is really small, it means that that sample is unlikely given the population, which means that we reject the null. And if your p-value is large, then we're going to fail to reject the null. There is no such thing as accepting the null. And so the last thing that we talked about is a significance level, which is alpha. That's how we decide if our p-value is large or small. So a lot of times we take that alpha to be 0.05, that 5%, but sometimes you'll be given a different value instead. All of that sound familiar? Okay, where we ended is how do you choose that alpha? How do you choose that significance level? And you consider the consequences of making a wrong decision. And so we talked about there are two different kinds of wrong decisions that can be made. If we talk about a jury, if someone is on trial, one error would be letting a guilty person go free. And then the other error would be imprisoning someone that was innocent. And we talked about which error is worse is going to depend probably on the crime. If the person is accused of murder, we really don't want to allow the possibility that that person goes free if they're really guilty. All of that sound okay? Okay. Finally, what is new then is the two type of errors that can be made in a test. They are numbered. There is a type 1 error and there's a type 2 error, and normally they're given with Roman numerals. I think it's easier to remember a type 2 error. So here's how I remember a type 2 error. A type 2 error, type 2, you fail to reject the null. Now, that's not an error yet. That's just a decision. The reason this is an error is you fail to reject the null, but the null is false. That's what makes it an error. If the null is false, we should have rejected it. But if the null is false and we fail to reject it, that's an error. Something went wrong then. Okay, that means a type 1 then, instead of failing to reject the null, is rejecting the null. Again, that's just a decision, though. That's not an error. If we're rejecting the null should have been false. If this is an error, though, we're rejecting the null, but the null is true. Okay, here's what that means. If we reject the null, we find convincing evidence that HA is true when it isn't. So if we reject the null, it's because we find convincing evidence that the alternative is true. If we fail to reject the null, remember that does not mean we found evidence for the null. There's always evidence for the alternative or not enough evidence for the alternative. So if we fail to reject the null, we do not find convincing evidence that HA is true when it really is. And then I've said this a few times, haven't written it down though. Which error is worst? It depends on the situation. So we can't say a type 1 error is always worse or a type 2 error is always worse. It depends on the situation. Okay, let's do a quick example and then we're gonna move on. We're gonna describe a type 1 and type 2 error in the context of the CEO example. And which error could the researchers have made? Okay, the CEO example, if we remember, our null is that the proportion of corporate CEOs born in June and July is 2 out of 12. And then we were looking for evidence that that proportion was actually less than 2 out of 12. Okay. So, for our type 1 error, I'm going to show you how I structure this. What I do for type 1 and type 2 error, I first start by just writing a few words as to what that error is. So I told you I think type 2 is easier to remember because I just have to remember 2 is fail to reject the null. But if it's an error, that means that the null was false. Type 1 error, then, is I'm rejecting the null, but the null was true. Okay, so we have to write this in context, though. Rejecting the null means we find evidence for the alternative. So a type 1 error occurs when the researchers find evidence that the population proportion or the true proportion of corporate CEOs born in June and July is less than 2 out of 12. This is where most people stop. So most people will write this and put a period there. This is not an error. This is just a statement. If you read it again and just think of your own reasoning, researchers find evidence. That's all we've said. That's not an error. The reason this is an error is they find evidence of something that's not true. So all we've done is the reject part. We still need to make this a mistake. So researchers find evidence that the population proportion of corporate CEOs born in June and July is less than 2 out of 12 when this is not the case. That's what makes it an error. We've just said they found evidence of something that's not true. Okay, so then a type 2 error. If we fail to reject the null, again, that's always in terms of the alternative. If we fail to reject the null, it means there's not enough evidence for the alternative. So a type 2 error occurs if researchers do not find convincing evidence that the population proportion of corporate CEOs born in June and July is less than 2 out of 12. I'm going to stop right here. When I get to this point, I need to reread so that I know where I'm at. Okay, researchers do not find convincing evidence. Again, this is not an error, that's just a statement. All we've said is that we fail to reject the null. So we've just made a statement, we haven't made a mistake yet. So researchers do not find convincing evidence, blah, 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 when this is actually the case. A lot of times with these errors, you will then be asked the consequence of each error. In this case, I don't think there's any real meaningful consequences, but don't be surprised if you are asked to do that in your homework. So it's always find evidence of the alternative, even though it's not true. Don't find enough evidence for the alternative, even though it's true. So I'm going to be very picky on the way you word those. Questions on the way to word those? Okay, a few last things to talk about. The probability of a type 1 error is alpha. And it's the alpha that we've been talking about, the significance level. The other thing for you to know is the probability of a type 1 error and the probability of a type 2 error are inversely related. What I mean by that, if you increase the probability of one error, it decreases the probability of the other. Here's why that matters. A lot of times with these error questions, you'll be asked something like, would you prefer a test where alpha is 0.05 or where alpha is 0.1? And a lot of times people will say, well, I'm just going to choose the smaller one, right? If alpha is an error, I want the smaller error. But what you have to recognize is if we decrease the probability of a type 1 error, so if we make that one lower, the probability of a type 2 error will go up. So what you have to do is determine which error is worse. For example, if type 2 is worse, we can minimize 2 by, so if we want to bring type 2 error down, we have to bring type 1 up. So we can minimize the probability of a type 2 error by choosing a larger alpha, and that's because alpha is a type 1 error. This relates to something we did in probability. If you remember in probability, you guys did a question that had to do with drug tests. Do you remember talking about this idea that if you get drug tested at work and you test positive, the very next thing they're going to do is test you again? Okay. The reason they do that is they really want to make sure that that positive is actually true. What is the issue, though, when you give someone a second test? You remember? The false negatives increase as well. So you're by increasing the certainty that the person does drugs, you're also, well, I guess it's one error is going up and the other one's going down. That's what I'm trying to say. I'm just saying it very poorly. So you're increasing false negatives, but you're decreasing false positives. Okay, that's what we had to finish from 9.1. Okay, so now that we've talked about errors, we're going to get into, we're doing a test for population proportion. Let's talk about the background first. The first one is the 3 conditions for a significance test. They're pretty much the same as a confidence interval. What was the first one for a confidence interval for proportion? Really, any confidence interval. Random sample. Second one. Normality. I'm going to write it as approximately normal sampling distribution. How did we check that for proportion? So not central limit theorem. That's for mean. How did we check that for proportion? N times p hat greater than or equal to 10, n times 1 minus p hat greater than or equal to 10. And lastly, the 10% rule. Here is the only difference. So the only difference when you're doing a test is you are using p instead of p hat. That is the only difference. And that is because we are assuming that the null is true. So in the null, we're going to have the value of p. So then in a confidence interval, you use p hat. That's the only difference, though. That's it. Okay, test statistic. This is our calculation. It is related to a z-score. What does a z-score measure? Come on, guys, you know this. What does a z-score measure? Augie? Number of standard deviations from the mean. Okay, the formula that is on the formula sheet is in words. So we're going to write it down in words and then figure out what the symbols are. It says standardized test statistic is the statistic, subtract the parameter, all over standard error of the statistic. So similar to a confidence interval, there's a formula, but it's in words. So you have to be able to take the words, put them into symbols. Okay. Similar to when we did confidence intervals for proportion, the symbol that we're going to use is z. So we have z equals. The statistic is p hat. The parameter that goes along with it is p. And then if you were to look up the standard error formula, it's going to have p hat, 1 minus p hat, all over n. This is the part that's going to be hard to remember. You're not going to use p hat, you're going to use p. And that's because we have the value of p. We are assuming p to be true in the null. So that's what you're going to use. Okay, I need maybe 6 or 7 more minutes of time, and then we'll take a break. Colleen?
I still use p hat in the numerator.
Correct, yes. So that's the only place that p hat is going to show up. Okay, the 4 steps are the same. We're not going to write them down. It's still the 4 C's. Okay, what happens if the data or evidence don't support the alternative? Don't do the test. You are only going to actually carry out the entire test if you have evidence that supports the alternative. So we're going to do this quick example over the next, 6 or 7 minutes. We're not going to do the whole process. I'm just showing us how to do the calculations. Okay, according to an article in the San Gabriel Valley Tribune, most people are kissing the right way. That is, the majority of couples prefer to tilt their heads to the right when kissing. In the study, a researcher observed a random sample of 124 couples and found that 83 tilted to the right. Is there convincing evidence that couples really do prefer to kiss the right way? Okay. Here's the general idea. Start with, what are we looking at? So if we think of our null and our alternative, this 83 out of 24 is a proportion, which tells me that my null and my alternative need to be in terms of population proportion. The null will always be equal to. So is there convincing evidence of a preference? If there were no preference, we would expect about half to go to the right, about half to go to the left. So if there were no preference, we would expect p to be 0.5. We want to know, is there a preference? So is that population proportion greater than 0.5? P in this case is the population proportion of couples tilting heads to the right. And again, we don't know P. We have P hat. We have one sample, but we haven't looked at every single coupling. So then you're going to ask yourself, is there even evidence for HA? Well, the sample proportion is 83 out of 124, which is about 0.669. If we compare that to the alternative, that is in fact greater than 0.5. So yes, we do have evidence for the alternative. The question is, do we have enough evidence? So then if we look at what are our possible explanations? So why did we get a sample that was bigger than 0.5? We've talked about that. Either this is just a result of sampling variability, which means there is no preference, we just happened to get a sample that's greater than 0.5, or there is a preference. So either we just happen to get a sample proportion bigger than 0.5, or there really is a preference. And this is where we now do the calculation. That z from above means we're looking at a normal curve. So we always have the mean, the standard deviation, 2 standard deviations. The value we are assuming to be true is 0.5. That's our mean. So then to find the standard deviation, that's what was above. The P1 minus P all over N. That P is just the 0.5 that comes from the null. And our N is the sample size of 124. That calculation ends up being about 0.05. So this number is about 0.54. This is 0.59, just because the rounding is a little off. So this is about 0.46. This is about 0.41. So this 0.669, if we find that on the graph, that's like way over here. And greater than in the alternative means we're shading greater than. We're not actually going to calculate this probability, but can you tell based on the 0.669 and the 0.59 that this is going to be pretty far away? And that this probability is going to be really small, like probably close to 0. So if we were to do the calculation, we would end up finding a p-value pretty close to 0. So in our mind, what we're thinking then is, okay, that p-value of 0 is less than our alpha, which we're just going to call 0.05 since we don't have one, which means it is incredibly unlikely, if the null were true, that we would get this sample proportion. So if the null is true, it's highly unlikely we would get this sample proportion. What does that mean? That means we have evidence to reject the null. This is the very, very bare bones of a hypothesis test. After our break, we will go through the whole process. But this is just the basics of carrying out the test. Questions for me before our break? Okay, so now that we know the quick background, let's go through an actual problem. So here is the one we're going to do together. When the accounting firm AJL and Associates audits a company's financial records for fraud, they often use a test based on Benford's law. Benford's law states that the distribution of first digits in many real-life sources of data is not uniform. In fact, when there is no fraud, about 30.1% of the numbers in financial records begin with the digit 1. However, if the proportion of first digits that are 1 is significantly different from 0.301 in a random sample of records, AJL and Associates does a much more thorough investigation of the company. Suppose that a random sample of 300 expenses from a company's financial records results in only 68 expenses that begin with the digit 1. Should AJL and Associates do a more thorough investigation of this company? So we're going to do a hypothesis test. It's still the 4 C's that it was before. So if we start with choose, we have this 68 out of 300. We have this 0.301. Both of those are proportions. So P is going to be the true proportion. What are we looking at? We're looking at of the expenses that begin with the digit 1. So P is the true proportion of expenses beginning with the digit 1 for this company. We don't know the company name, but it's some company. So then we're going to need our null and our alternative. Both are going to be about that P. The null is always equal to. Okay, so if there's no fraud, what we expect is the proportion of expenses beginning with the digit 1 to be that 0.301. And then the question is, should AJ Allen Associates do a more thorough investigation? It says that they're going to do a more thorough investigation if the proportion is different from 0.301. So that's not greater than or less than, but that's not equal to. Okay, and then we have to say what we're going to do. So this is still in the choose step. We are going to perform a two-tailed, one sample hypothesis test for proportion using Z, and sometimes you're given alpha. If you're not, we're going to say that it's 0.05. So a lot of that stays the same. Really, the only thing that's changing here, this two-tailed comes from the alternative. But otherwise, it's always one sample. You're always going to say hypothesis test. You're always going to say proportion. Proportion will use Z, and alpha will be 0.05, or you will be given alpha. The other options, like we talked about, could be upper-tailed or lower-tailed. That's all to choose. Okay, we're going to take a quick pause here. There's no reason to do the test if we do not have evidence for the alternative. So right now, we're just going to do a quick little check. Do we even have evidence for HA? Well, the sample proportion is 68 out of 300, which ends up being about 0.227. Well, that 0.227 is definitely not equal to 0.301. So yes, we do have evidence for HA. We got a proportion that wasn't 0.301. At this point, if we had gotten a p-hat that was 0.301, we're done. There's no reason to even carry out the test. What is in yellow, you do not need to write. Just do a little mental check or a check in your calculator. Okay, now we need to check our conditions. First one, we need to know, is it a random sample? Okay, so it says, suppose that in a random sample of 300 expenses. So yes, we have a random sample that is stated. You need the word sample. Saying random is not enough. Second assumption, we need an approximately normal sampling distribution. You do not need to put this in symbols. You can jump right to numbers. So it's n times p. Our sample size is 300, and then you're going to go back to the null. So you'll take that 300 and you'll multiply by the value of the null, which gives us 90.3, which is yes greater than or equal to 10. And then you'll do 300 times 1 minus 0.301, which gives you 209.7, which, yes, is greater than or equal to 10. Again, you don't need to put symbols there. If you're going to put symbols, though, they need to be correct. And then lastly, our 10% rule. We need our sample size to be less than 10% of the population. When technically do we have to check that? Because it's not all the time. It's only when we're doing what? Only when sampling is done, which in this case we're sampling expenses from financial records, so we do need to do that. Our sample size is 300, which means our big N has to be larger than 3,000. Now, I don't know if that's true. I know nothing about this company. So I'm going to say I assume there are more than 3,000 expenses at this company. Okay. Calculate is when things end up being the most different from a confidence interval. So this is where we're going to calculate our test statistic. So that's the formula we wrote down before. Z equals statistic, so p hat, subtract the parameter, which is p. And then you have that square root, and you just got to remember to use p and not p hat. Okay, so what I want you to notice is this is the first time that p hat is used. P hat is not used in the check step or in the choose step. So a lot of people use the p hat too early. This is the first time it comes into play. And that p hat is the 68 out of 300. And then the p just comes from the null. So that's the 0.301, and then the square root, 0.301, 1 subtract 0.301, all over n is 300. Okay, right now I want you to put this in your calculator because I want to make sure we all get the right number here. So take a minute, plug all of that in. You can plug it all in at the same time if you use your parentheses wisely. What I mean by that is I would put the numerator in parentheses, and that should be about it. That should give it to you. Okay, so we should have gotten about negative 2.807. Okay, so then let's talk about what this means, because we need to find a probability. So this is a z, so this is a normal curve. So we have the mean, 1 standard deviation, and 2, -1, -2. So negative 2.807 is the number of standard deviations away from the mean. So that is about here, negative 2.807. Now, we've talked about you're finding an area. So we're not finding the probability at one specific value. You're finding an area. And so the question is, which way are we looking for the area? This is going to go back to the alternative. So our alternative is not equal to. which means you're going away from the center. Away from the center. So what we're going to do is we're going to find this. But then the two-tailed test means we need the symmetric part on the upper side as well. So we need the symmetric part on the upper side as well. So we're also going to look to 2.807 and above. Now, those are the same areas. So really all we're doing is we're finding one area and we're doubling it. On our calculators, we would go to normal CDF. So what I'm doing, if I'm finding this one, I'm finding the probability that z is less than or equal to negative 2.807, but then I'm going to double that because there's two tails. So please right now make sure that you know how to do this on the calculator. You're going to go to normal CDF. Our lower bound is a big number, and we're going up to negative 2.807. That's a z-score, so we can just put a 0 in for the mean and a 1 in for the standard deviation. And then whatever you get, you're going to double it. And you should be able to tell from the figure that it's going to be a small number. It's about 0.005. That number is the p-value. So that is the probability of this sample proportion if the null were true. So that is the probability of the sample proportion we got if the null were true. Questions for me before we write a conclusion? Okay, so finally, the last C is we are going to write our conclusion. Like the hypothesis test, there are two sentences. The first one is just what is our decision. And so what we're going to do is we're going to take this p-value, the 0.005, and we're going to compare it to alpha, 0.05. Because our p-value is less than alpha, we will reject the null. You have to show this inequality. If you do not show the inequality, you're not going to get credit for the conclusion. And now we need to say what that means in context. So I reject the null. And if we reject the null, we believe the alternative. So I reject the null and instead believe the population proportion of expenses beginning with 1 is different from 0.301. That's just the alternative in words. So what we said in simple terms is we reject the null and we believe the alternative. You also are going to be asked each time to interpret the p-value. The p-value is the likelihood of the sample we got if the null were true. So I'm going to say, assuming the population proportion of expenses beginning with the digit 1 is 0.301. So assuming that p is 0.301, there is a 0.005 probability of a sample proportion of 68 out of 300 or more extreme by chance alone. And these are just the sentences that we've been writing. I'm going to move, but I will come back. One thing that we sometimes have to look out for is there a question that was asked? So here we are asked, should AJL and Associates do a more thorough investigation? So we need to specifically address that. We haven't answered that. So this is asking, is there evidence of fraud? There's evidence of fraud anytime the proportion of first digits is significantly different from 0.301. That's what we found evidence of. So the very last thing that we need to do is actually address that. So what I write is ATQ. So if you ever see me write that, that means answer the question. And all I'm going to say is yes, AJL and Associates should do a more thorough investigation. Bless you. Questions for me? I'm fully aware that this is a long process, so this video will be on Schoology if you need to refer to it when you're doing your homework. When you're doing your homework, remember it's not going to say the 4 C's, it's going to say something else, but it's the same general process. Questions before we talk about the last few things? We just got 3 more things to talk about, and then we're done. Okay, next page. Can you use confidence intervals to decide between 2 hypotheses? What is an advantage to using confidence intervals, and why don't we always use them? What I need you to know is that confidence intervals give us more information because they give an estimate, right? A hypothesis test is only a yes or no, whereas confidence intervals give us an estimate. But, and this is the big reason we don't always use confidence intervals, but a confidence interval can only match or answer a 2-sided or a 2-tailed test. So in the example we did, it was 2-tailed. We could have answered the same question using a hypothesis or using a confidence interval. But if it was greater than or less than, we couldn't. So here would be an example. If we used the same data from that example that we just did and did a confidence interval, this is the confidence interval that we would have gotten. And so if we ask, does the interval provide evidence that the company should be investigated? We're going to say yes. What are we looking for in the interval? We want to know, is it possible that P is equal to 0.301? No, that's not a reasonable estimate based on the interval. So, yes. we should investigate. It does not mean that there's fraud, but there's evidence there could be fraud. I forgot to say something on the last page. I don't want to go back here because it's going to mess up the recording, but can you guys go back to the hypothesis test that we just did? A lot of times, you will be asked a follow-up question, so I want you to just write this at the bottom. So go back to the hypothesis test we did, just write this at the bottom. You might be asked something like, could AJ, L, and Associates have made a type 1 or type 2 error? Type 2 error, remember, is when you fail to reject the null, but the null was false. Type 1 error, you reject the null, but the null was true. We went through the whole test and we rejected the null. So if one error was made, it could have been a type 1 error because we rejected the null. Okay, last thing that we're going to do right now is I'm going to show you how to verify this on the calculator. So can you use your calculator for the calculate step right now? No. Right now you're using it to check only. Later, yes, you can. By later, I mean May. Right before the AP test, I'm going to have you stop showing all the work and just use the calculator. So right now, I want all of the work, like showing all of the substitutions, getting your test statistic, getting your p-value, then you can check on the calculator. I'm going to talk us through how to do this. I'm not going to show a calculator up here, though. So I need you all to be really on top of your game with going through this. Where do you think you have to go on the calculator? Stat. Do this right now. Everybody do it. Hit stat. And then you're going to go over to tests. Now, you're going to be really tempted to choose z-test at the top. And if you click on z-test, it's going to give you some things that don't make sense. So remember I told you on the calculator, if it involves proportion, the calculator will say proportion. So look down the list. Which one do you think is the one that you want? What, Veronica? One prop z-test. So if it's for proportion, it's going to say proportion. So you go down to one prop z-test. Okay, the p, like this, that just means the null value. So for us, that's 0.301. X is the number of successes, which in this case is 68. N is our sample size, which is the 300. And then you're going to choose not equal to. And then you'll see you have two options, calculate and draw. Let's do the calculate first. So go down and highlight calculate and hit enter. And you should see you get the same p-value, or the same z, and the same p-value we got. It should say z equals negative 2.80687. And below that is the p-value, 0.005. So the expectation is you do the whole hypothesis test, then go to your calculator and check it. Go back, do the same thing. So go back to one prop z-test, but hit draw this time. And it should draw you the normal curve. Do we see that? And you should see there's no shading. That's just because the area is so small. And below that, you'll see the test statistic and the p-value. Any questions, comments on the calculator? Veronica?
Error for the drawing.
Okay, if you get an error for the draw, there's something somewhere else in your calculator that doesn't like, probably in y equals. So I would hit the y equals button and clear those out, and then it should work.